So the ancients knew the size of the Earth. Who knew? No, I just said it. The ancients knew. People have known for a really long time. Just because that information was lost in Western civilization during the Dark Ages doesn't mean people didn't know it. Here's another one that's pretty amazing. Did you know that the ancients had a decent idea of the distance of the moon? Yeah, go out and look at the moon tonight and tell me how far away you think it is. Here's a way that it could be calculated. Now, one time that the Earth and moon interact in a way that we can visually see is during a lunar eclipse. Now, I know that you know that a lunar eclipse occurs when the moon travels through the Earth's shadow. And if we knew the size of the Earth, could we not assume we knew the size of the Earth's shadow? Well, yes and no. There's really two parts of the Earth's shadow called the umbra and the penumbra. But for these purposes today, we're just going to talk about the Earth's shadow. Now, since the ancients knew the size of the Earth, they basically knew the size of the Earth's shadow, which would be twice the radius. Now, during a lunar eclipse, what happens during a lunar eclipse is that the moon actually enters into the Earth's shadow. I know you know this. So what we actually would see would be as the moon is entering, it becomes darker on one side until finally it passes through the penumbra and is into the umbra and is in the darker part of the Earth's shadow. Now, the distance that it takes from the moment it first enters the shadow, this front edge, until the back edge crosses and it's completely in the Earth's shadow, you know how far it traveled at that point? Yeah, I don't know the number either, but I do know that it's equal to the diameter of the moon. Whatever distance it traveled, it was the diameter of the moon. Now, as it continues to go across the Earth's shadow, it'll stay dark, no apparent change in brightness until on the other side, it finally starts to see the light. During the time it took from when it entered until when it left, how far did it travel? Yeah, do you see it? I know you do. It traveled the diameter of the Earth. I bet you see it better than you see the writing that I just made. Now, on this handout, it says it takes 5 minutes to enter and 18 minutes to travel through the entire shadow. Those numbers are just made up. That's a lowest common denominator. Really, the time elapsed is closer to 53 or 54 minutes for the moon to enter the Earth's shadow and over 3 hours for it to leave. All right, so let's do it. Let's calculate the size of the moon. That's amazing. Let's set it up. So if we have the diameter of the moon is going to be equal to the diameter of the Earth times this ratio of 5 to 18. Now, the Greeks would have known the diameter of the Earth here we go, times 518. And they were able to obtain a value 3.53 times 10 to the 6 meters. And if I divide that by 2 to find the radius, I end up with 1.77 times 10 to the 6 meters. I know you're thinking, wow, what's the big deal? The big deal is that moon that you see in the night sky, it's really hard to tell how big it actually is. But the Greeks were able to use a lunar eclipse and their understanding of the size of the Earth to actually calculate the size of the moon. If that doesn't blow you away, you're not paying attention. All right, that's piece number 2. Piece number 3 to the puzzle is coming right up. Okay. The last piece of the puzzle that we need is, if we know the size of the Earth, we know the size of the moon, the question we need to get into so we can talk about Sir Isaac Newton, is how far away is the moon? Well, let's check it out. The calculation is actually pretty easy. If you could write down on a piece of paper, how far away is the moon? And we can do a really simple calculation using arc lengths. Let's do that. So let's imagine ourselves standing on the surface of the Earth. Diagram, not to scale. Looking up at the moon and the night sky. Now, the size of the moon has been known since antiquity. We'll let the size, or the diameter, be 3.53 times 10 to the 6 meters. Now, if I were to go ahead and draw in a line from a place on Earth to each side of the moon, it would look a little something like this. All right, so if we were to draw those 2 lines in, those red lines are going to represent the orbital radius of the moon. How far away it is from the Earth. Now, to measure that angle, 1/2 degree, is actually very simple. If you were to take a device, it could be as simple as 2 meter sticks, and hold them up such that you were to eye each side of the moon in the night sky, you could measure that very small angle. Now, that angle of 0.5 degrees to a circle of 360 degrees, well, that angle gave us an arc length of 3.53 times 10 to the 6 meters. So what would be the circumference of that circle? Well, we can calculate that easily enough. Let's do that. And I have a pretty unbelievable number of 2.54 times 10 to the 9 meters. Now, if that's the circumference, to find the radius of that, 2 pi r, I just take this value of the circumference and divide by 2 pi. Make sure you put that 2 pi in parentheses when you plug that into your calculator. And the radius of the moon's orbit is going to be 4.0 times 10 to the 8th meters. Yeah. Now, here's the kicker. You want to know what the accepted value is? The accepted value for the distance of the moon is 3.8 times 10 to the 8th meters. Yeah, it's going to be less than 5%. And here's the thing. I know by now you're starting to tune me out. That's okay. I'm not listening either anymore. But I want you to go out and look at the moon tonight and tell me that you had any sense that these numbers would really accurately depict what's happening. The moon is much, much farther away than we realize, and it's much, much bigger than it at first appears. But you know who did know? The ancients. You know who used that information to demonstrate the universal law of gravity? Newton. And that's where our story will pick up next time. Thanks.